for this?
Yeah, so Mustafa's ill, unfortunately, and he did most of this work, and they're his slides, so just bear with me. So this work we did a few years back, but I think in the time since then, when we've applied GANs to other problems, actually this was one of the ones that worked the best straight away. So it gave us some initial optimism that perhaps hasn't been brought out, but at least for this case, it works very well. So, I mean, a lot of people have talked about this, generative models for emulating scientific data. In many cases in science, we have an existing simulation that uses a direct physical model. And, when we started this project, we really wanted to just see, can a generative model, can a GAN, how close can it get to generating a similar distribution? So, the motivation within cosmology, as many of you here, of course, know, is, there's an inverse problem, and one way of solving this is to generate these simulated, virtual universes, as it's sometimes called. So our target is these cosmology convergence maps. So this data is produced both through n-body simulations and then a process of ray tracing to produce these maps that can then be compared with sky images. And there's this motivation here for weak gravitational lensing is an important area, and these maps are an important part of that. So producing these normally requires not only computational intensity, but also quite a lot of human time to tune various parameters and so forth. So generative adversarial networks have been introduced. You have two networks working, sort of against each other, sort of together. And we actually found that using the sort of initial DC GAN, one of the early architectures used, and the conventional loss, actually worked very well for this problem. And our motivation was really not to vary too much from sort of standard things when they can work well. We have since then used WGANs and so forth and actually found that this gave us the best results overall. But one area where we did involve a little bit, so our general motivation was not to be physics motivated, unlike some of the various projects described here, but really to try and recover the physics from something just a full-on deep learning approach. But one area where we found it was important was in the training methodology, where GANs can be unstable. So we had a sort of ad hoc procedure where during the training, we trained for a number of epochs, but then stepped through via iterations and calculated some summary statistics to then use that as a further constraint. But that, as I described, is a sort of ad hoc procedure, so I'll come to some areas for future work afterwards. So here's the sort of training going on, and that's actually the start. And then you can see initially it starts off with random noise, and then there's some strange structures appearing, and then you end up with very realistic looking maps. So here are some map comparisons. On the top is validation, and on the bottom are the generated maps. And by eye, even to a trained cosmologist eye, they look very similar. But then we can start to compare actual statistics. So here, this is just the count, so the pixel intensity. And you see over various orders of magnitude, it still agrees extremely well. But the GAN was trained to reproduce this. More interesting to cosmologists is the power spectrum, which is the Fourier transform, the two-point correlation. And you can see here that, so the bands, so I don't know if there's a pointer. Yeah, so not only does the GAN able to reproduce the mean of this distribution very well, but also the uncertainty bands are also reproduced. So the black is a validation data set that's completely independent, and the GAN reproduces all this structure. So we were interested, so you can also probe this further by taking slices and calculating the p-value of these histograms. They obviously agree, as you can see there. But we were also interested in seeing where it might break down. So this is actually a correlation matrix of the power spectrum here. And so you can see for the validations data set here and the GAN on the face of it, they look the same. So again, you might think they're the same. But if you actually subtract them and use an auxiliary data set that's completely independent, again, data set from the validation as well, then there is some structure here between the high and low L's that you can see that's different between that in the auxiliary data set. So this was really trying to expose the differences. Some other, you could actually restrict the range of L that you were interested in, and you wouldn't see this structure. But we did manage to find some interesting differences that are sort of washed out on this plot, but you can see it on my screen. Okay, so the power spectrum is a two-point correlation, so you might think, oh, it's just able to reconstruct that. But actually, what's interesting also cosmology-wise, is 3-point correlation, and this Minkowski functionals are related to that. And again, you can see that the GAN was able to reproduce these extremely well. And again, you can take the slices, and the p-values are high. So one obvious question with GANs in general is whether by the procedure it's actually parroting back the training data set that you use. And there's various ways to explore this. One way is interpolating in the latent vector z that was used to generate these. Between two values of z, you can see, does the distribution vary smoothly? And it does. You get like independent maps varying smoothly between these. So these are shown in, like, for example, the classic GAN training on celebrity images when they morph from one celebrity to another. This is the cosmology equivalent of that. And it seems to pass that test at least. And another test is to compare, to take those that are generated and look at those that are closest in the training data according to some metric. So here we use the L2 on the pixel intensity to find the closest map, and then compare the power spectrum for that. And these are distinct maps, not those in the training set. And also you can do that the other way, which is to use the closest power spectrum map in the original training data set and see that these are actually distinct looking images. Okay, so that works pretty well, and that really is the Cosmo GAN in action. But really, what is the ultimate goal here is to build an emulator using GANs to be able to parameterize and produce new maps that were different to the other. Initially, trying to interpolate so that we have a fast emulator, and then we can use that to go back and generate full simulations. So, where we normally pass in the model parameters to the physical model or to the generative model, instead we can pass a parameter space. And obviously this wouldn't work if the model was discontinuous, but in our case there are smoothly varying. So now I just come to future work. Actually, I'll catch you up on time, I think, quite easily. So I mean, basically now we have some new blood. Actually, Peter in the audience who can solve these problems for us. As I mentioned, GANs are notoriously difficult to train, and they can be unstable in various ways. We had an ad hoc procedure to solve that for this case, but to move to the conditional case where we want to be able to vary the input parameters, then we found it's really necessary to stabilize this training, and we have a couple of approaches at the moment that we're exploring with spectral normalization and Jacobian clamping that are kind of current state of the art, if you like, in the field, and also self-attention. But I think also in order to really generalize beyond the training data set, not just do interpolation, but potentially extrapolation, we can use many of some of the ideas that have been discussed here and using physical constraints. And so our goals remain to do this parametric conditional GANs, but also to move. So there's other work. We've scaled up this to larger and larger images and also run distributed training. But really, to push this further, we'd like to be able to generate the 3D initial n-body simulations that went into producing the cosmology maps, which can not only be used for this purpose, but also for other cases that you would use those. So I'll come to my summary. So I think I showed that GANs can generate these cosmological convergence maps with high confidence, not only in the sort of initial pixel statistics, but also in the Fourier spectrum and in these non-Gaussian higher order structures. And so, it's clear, I think, that from all this and various other projects that deep generative models have the potential to create these kind of inexpensive emulators. But we do need more. We still need, even though we've been saying this for a couple of years, we still need more reliable training methods and better ways to incorporate conditional that really reproduce the same sort of fidelity, but also allow us to be conditional. Okay? I knew no one would complain if I was early.
No, great. Thank you very much. Let's give him a hand.